Let's continue our story of ridiculously big numbers with where we left off was we had the up arrow, the multiple up arrow notation, and we got as far as imagining maybe 1,000 up and then 1,000 up arrows and then 1,000, and that would be in terms of 999, etc. And then we thought about towers. After all, this all started from towers of exponentials. Well, what if you did iterated towers of up arrows? And the problem is this is getting ugly. How do you write this down elegantly? And so how could we codify this idea of taking a previous procedure and doing an iterated tower in a nice way? Okay. And it turns out that Conway came up with a nice way to do this. And really I'm taking this a lot from the Wikipedia article called Conway chained arrow notation. So a chained arrow notation is like this: numbers separated by horizontal arrows. And I'm going to give you the formal rules for it, and then but go quickly to examples. So here's the four rules. Three of them are kind of base case things, and then one of them is the essential recursive idea. If I just have p, that's just a number. If I don't have any arrows, that's just the number itself. Two numbers separated by arrows just represents an exponent. So 3 arrow 4 is just 3 to the fourth. Kind of like a vertical arrow or a caret would be. Exactly like that. Now, if I have any chain, so a bunch of numbers separated by horizontal arrows, and then a number and then 1, we can just strike off that number and make a shorter chain. So the goal of unpacking these guys, and it's going to be quite a bit of work to unpack some of these, is one of the goals is to make shorter chains. The other goal is to take this number and decrease it. And here's the key rule. If I have any amount of chain, like the 3, 4 here would be the x, although to take us a minute to get to examples that have 4 things in them. And then a number p, and then a number, which I'm going to write as q plus 1, because I'm going to want to express that in terms of chains that have a q in it, a 1 less number. What you do is this p is basically controls how many repetitions you do of the 1 less rank operation, the operation with a q at the end. So I think of this as like a nesting degree or an order or a degree or something like that, and p as a repetition control. So you write down whatever this chain is, like here would be 3, 4, repeatedly, and then you chain them with 1 less number at the end, q's. Now these parentheses are really, really important. So for example, you might think, why am I putting parentheses around a single thing? Well, that means evaluate this thing. If it's a number, it just means the number. If it's a chain, you need to figure out what that chain is first, and then that's going to go into another chain where this is now the repetition controller, and then that goes into another chain where this thing is the repetition controller, etc., etc., etc. And then you're going to get a chain with a bunch of things with q's in them. That's 1 less than what you started with, and then hopefully you'll be able to figure that out in terms of q minus 1, etc., etc. Now, if you want a recursive version, this dot 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 is still a little inelegant from the point of view of recursive definitions to say, I'm going to repeat this and I'm going to have p x's. That's what I meant by saying p is the repetition control. You can make that a little bit more official by saying if it's 1, then you don't really repeat much of anything. You just write x down, and that's it. That's basically what this is. And then if I have x and a certain number of repetitions to a certain number of the degree controller, that just means if you've already written down what it means to expand out x with p repetitions and the q plus 1 controller, write that down, and then put an x in front of it and a q at the end of it. So that's basically, if I've already got this much of the expression with p minus 1 x's, then I just put another copy of x at the start and a q at the end. A typical thing about recursive definitions. So we're getting a little more sophisticated here, but I hope that's okay. But I'm still going to concentrate on the examples. Okay, so there's our rules, and now we're going to do some examples. Let's just do almost the simplest non-trivial example with just a 3 chain and a 2 at the end. So the rule is I write down a sort of nested chain here with 3, this number is 3, so 3 of this number, 3 4s, 4 arrow, and then parentheses 4 arrow 4 arrow 1 arrow 1. And so this is a 2, and so this is a sort of something at the 2 degree level, but it's expanded out in terms of things with the 1 degree level. Now 4, that's just the number 4, so I just evaluate that. And then the rule is when I get down to the 1 degree level, that's really just the end of the line for this kind of extended chain. And I make the chain shorter. 4 goes to 4. And then the other default rule for the base case rule is that that's just exponentiation. And then I can chop off this one as well. So I get 4 arrow 4 to the 4. Oh, that's 4 to the 4 to the 4. Well, not a coincidence. This replicates the Knuth notation. This is 4, 2 up arrows 3, because I'm doing an iterated tower of exponentials. There's 3 of them, and the number is 4. Okay, so in fact, this is going to work for any number and then a 2. What we do is we write down b of this number a in this nested form, and then these all decrement to 1s. So the 1s can all be chopped off, and then I just get a arrow a, which is a to the a, and then a arrow that, which is a to the a, and then a arrow that, and a arrow that, a arrow that. And so in fact, what we're getting is that this notation just really does replicate the double up arrow. Number, arrow 2 is just the double up arrow. In fact, turns out that when you have a chain with exactly 3 numbers, it is exactly the Knuth up arrow notation. It's the it's r arrows put between this number p and this number q. So a couple of examples of that. I'm not going to do a full recursive proof. That's not the point of this kind of thing. So 5 to 4 to 3. So I'm going to expand that out. That means I'm supposed to write 5 4s in this nested sequence of chains, and these guys are supposed to be knocked down to the 2 version of the arrows. Okay, so we just figured out that number 2 is a double up arrow. So I'm just going to write it that way. That's 5 double up arrow 5. Now that's being put into another 2 arrow machine. In other words, a triple arrow machine where the last number is 2. Well, guess what? 5 number 2 is just 5 double up arrow whatever this number is. So that's 5 double up 5. And then that's getting put into the 2 machine, the machine with a 2 at the end, and we know that's a double up arrow machine. And let's guess what we get. We get recursive or iterated double up arrows, and there's 4 of them. So we get 5 triple up arrow 4. Now, again, we're getting to really, really huge numbers here. Stop and think a minute. I mean, this can be very formal, and it's just like this sort of very, very formal mathematical game. But the whole point of these videos is these are huge numbers, and it's fun. 5 triple up 4 is really, really big. Now, it's not as big as we've gotten before. It's not as big as like this stuff. Don't worry, we'll get there pretty soon. Conway notation takes you there pretty soon. Okay. So, what's the next one? Okay, 7 to 5 to 4, let's say. So that gets expanded with 5 7s, and these guys are now the 3s. Okay, so 7 7 3. Hey, we just figured that out. Number 3, I think we can be pretty sure that that really is this is going to be 7 triple up 7. And where does that get put in? It gets put into exactly a triple arrow situation with a 3 at the end, which is what we know how to do. So that's 7 triple up the quantity 7 triple up 7. And then that gets put into a 7 blank 3, so it's 7 triple up that whole thing, and then that gets puts into that. And how many are there total? There was always 5 7s here in every single line, so it's 7 quadruple up 5 because it's an iterated triple up. And the reason for that is the 4, the arrow combination with the 4 at the end gets expressed in terms of arrows with the 3 at the end. Okay, so these rules so far are exactly just another way to say the Knuth rules for operating these guys. So, but the question is, what is this bias beyond Knuth? I'm claiming it gets way beyond the Knuth notation. So let's try a 4 chain. This is where it's going to start to blow up. 3 to 3 to 3 to 2. Okay. So now is where we really have to remember this rule that when we have the expansion rule that knocks this down by 1 and makes the chain longer, or the expression longer anyway, this comes in as a unit. So it's 3 arrow 3, and then 3 arrow 3, and then 3 arrow 3. That's repeated 3 times. That's the repetition controller. And then just these guys get knocked down to 1 at the end. So that's going to make it somewhat simple. Okay. So that's 3 arrow 3, 3 arrow 3, 3 arrow 3, just knocked off the 1s. Hey, that's just 3 to the 3. And we know what this is. We know what all the 3-term arrows are. They are exactly Knuth notations. They're exactly multiple up arrow notations. This is 3 with 3 to the 3 up arrows. That's 27 up arrows, 3. Okay. And then that gets put into another triple chain. So it's, you take this number, which is already unbelievably huge, 3 with 27 up arrows, and then 3. And then you make that the number of up arrows for the next calculation. Wow. And really, that's the heart of this whole thing, is this idea of take one huge calculation and then put it into the most sensitive parameter of the same kind of calculation, but just the next version of it. And that's that idea of recursion. Okay, so let's do another example. 3, 3, 5, 2. And I'm only putting a 2 at the end, you might notice. Okay, so 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. There's 5 copies of 3, 3. And then the 1s just go away. And so 3 arrow 3 becomes 3 to the 3. That becomes the exponent of the arrow in 3 up arrow something 3. That becomes the exponent of the arrow here. That becomes the exponent of the arrow here. That becomes, and what we've gotten to is exactly what we got to at the end of the previous video. This idea of cleverly putting in and having an iterated tower where we always put the result of the old calculation in the sensitive spot, the superscript on the arrow. So, in fact, that thing that we ended up the last video with was nothing but 3 arrow 3 arrow 20 arrow 2, which doesn't look so intimidating anymore. It's just got these very moderate-sized numbers. It's not hard to write down, and yet it encodes this ridiculous idea of taking Knuth notation and iterating that in the most powerful way. But what if you had a 3 at the end of our chain? We haven't even gotten to that. So 3, 3, 3, 3. Okay, so you do 3, 3, 3, 3, 3, 3, and then 2s. Okay, well, what is this? 3, 3, 3, 3, 2. That's 3, 3, 27, 2. Remember, the biggest number we got to at the end of the last video was 3, 3, 22. This is going to be quite a bit bigger because I'm going to repeat that. It's going to be a nested tower. I've got a dot, dot, dot in here. It's do this 3 up arrow, 3 up arrow, 3 up arrow, 3 up arrow, 27 times. Put 27, I guess there's probably 26 up arrows in here, but 27 3s on the left-hand side. Do that iteration just to get this in parentheses. Then that is the iteration parameter for how many times you do it again. So this is again 3 up arrow, 3 up arrow, dot, 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 okay, and then that closes out with a 3, 3, 3, etc. And how many times do you do it? You do it this many. You do that tower. Oops, sorry. That's not what I wanted. It's this many times. That's what's hidden in here, is you do that tower this ridiculous number of times. And all that is 3, 3, 3, 3. It's just 4 things separated by arrows, and the numbers are no higher than 3. What the heck? What about a 5 chain? What if this were just a measly 2 here? 3, 3, 3, 3, 2. That's 3, 3, 3, 3, 3, 3, 3, 3, 3. So now I'm repeating this whole triple block 3 times. And I got measly 1s at the end, so I can kill those off. Okay. So now, just inside these parentheses, I've got 3, 3, 3, dash something. Okay, the biggest I got to here, and this was utterly ridiculous, is a 3 at the end, where I took a tower of Knuth up arrows that was 27 tall, and then I used that to say how many times do I do a tower of Knuth up arrows. And now I'm going to take this number, okay, 3 dash 3 dash 3. That's 3 triple up 3. I can rewrite that. So that's 3 triple up 3. It's 3 to the 27. Okay, about a trillion. And I'm going to iterate this recursive procedure a trillion times of doing Knuth up arrows iteratively and making a tower, and then using that to describe how many things are in the tower, and then using that to describe how many things are in the tower, and then, and then, and then, and then. And then that ridiculous number is going to be put into the same procedure of one more time saying, let's make iterated Knuth up arrows over and over and over and over again this many times. Wow. Okay. Scary, ridiculously big. Okay. Well, I claim, guess what? It's still puny. But it's really, I mean, again, it's just amazing how big this is, and it's just not that hard to write down. So, if you want, if you don't want to do any more of these videos, if you just want a ridiculously huge number, just do 3, arrow 3, arrow 3, arrow 3, arrow 3, and then add one more. Think about how big that is. because that kind of recursively does all this stuff over and over and over and over and over and over and over again. But we'll go further in the next video.